Okay, hello, my name is Alexey Karnaev, and the topic of my research connected with machine learning and its application to diagnosis systems. In general, the main idea in machine learning and in artificial neural networks is the same as the main idea in, let's say, linear regression. In linear regression, the main idea is to model relationship between two sets, X set, an input set, and Y set, an output set, and this can be achieved by minimizing the loss function that highlight the difference between predictions and true values. And usually we use some kind of gradient descent method and trying to find the parameters, theta parameters in this case, two parameters in this linear equation that best describe the data that we study. And as the result, we have some program that allowed us to predict new values. The same idea works in artificial neural networks. In this case, an input, for example, an image of 9, can be transformed to an X, some metrics. Then these values go through the neural network, and the network answers in form of matrix hypothesis that and each element of this matrix is the probability of number. This is the probability of 0, probability of 1, and so on, probability of 9. And these values can be connected, let's say, with true values, and then the same way we should calculate the loss function and minimize theta parameters. And the number of theta parameters in artificial neural network is much more, definitely. And also we can use a lot of types of data when we study the diagnosis problems. We can use images or sequences of numbers or whatever, or even three-dimensional images, videos, and so on. And the main idea that artificial intelligence, modern artificial intelligence methods are based on machine learning, and the top of these artificial intelligence methods is deep learning that connected with feature extraction in neural network. Okay, and we know that today, and it is a very known fact that artificial neural networks can solve recognition problems even better than human do. And there are a lot of architectures of deep networks, shallow networks, and we may say that I can say that this is a kind of puzzle. We can construct any new type of network. And by the way, I should highlight that there are some problems. For example, the artificial neural networks may be confused sometimes. For example, when the inputs differ in small details, and when the artificial neural network, let's say, see something new. Here you can see an example when the picture presents banana, and the answer is absolutely correct, banana. But if one adds something new, something unusual element in this picture, then the network may be absolutely wrong, toaster instead of banana. And the same problem we can see in diagnosis system, and we try to solve them. In classics, there are three stages in diagnosis procedure. First stage is data collection. Second stage is artificial feature extraction. I should say that in modern system, this step is usually deals with artificial neural networks too. But in classics, people extract some features using, for example, frequency domain analysis and something like that. And the final stage is health state recognition. This is definitely machine learning or artificial neural network. In our research, the first stage was connected with experiment and the test rig. Here you can see the rotor machine operated with journal bearings, and we have multisensory measurement system that includes proximity probes, accelerometers, contact resistance sensor, flow meter, pressure sensor, and so on. And they all was connected in the measurement system based on National Instruments chassis and Pulse Type C Vibra analyzer. And we studied we studied 6 cases, 6 classes of rotor machine condition. First class is normal, when everything was fine. And then we studied several cases, several classes of mount failures. We decreased the torque on the bolts here, here, and here, and its combination. And by the way, we used one more class when the rotor has small additional mass that makes it unbalanced. So we had 6 classes, including 1 normal class. Then we collect this data from these sensors in different forms, like raw data and pre-processed data using FFTs from microphone and vibro accelerometers. And then we collected into samples. We took some small region of measurements from each sensor and collected in the sequence of data from multiple sensors. And even we try to represent it in form of figure, just like this, just like a carpet in this case. So sequences or images we used as the input data. And at the stage of preliminary feature extraction, we used autoencoder that looks like a bottleneck. In this case, the input data, I mean, not the input data, I mean that in this case, the network, the network have to realize which elements in the data are important and which elements are noisy. And in this case, this network works like a filter. Then in the final stage, file diagnosis, we used different architectures of neural networks for that is, we used one-dimensional convolutional neural networks with autoencoder. We used multi-layer perceptron, that is the simplest architecture, and long short-term memory networks that are good in work with sequences. And we realized that this simplest model works fine. And we checked our models in solving 2 problems. First problems was anomaly detection. We tried to recognize is this condition normal or some kind of failure, 1 of 5. We didn't think about which exactly. And the second classification problem was classification with 6 classes. And we get the results. 2 classes classification has very high accuracy, about 100%. In case of 6 classes, the accuracy a bit lower. And then we ask ourselves, is it high enough or not? Those 2 numbers, 97% and or 83%. And we checked this data with experts. We asked, I'm not sure, 5 of 6 experts. We show them labeled data first. We studied 2 classes, normal or abnormal. We demonstrate them labels first, and then we show them other images without classes and ask them to highlight these classes. And the accuracy of the expert was about 60%, maximum 65%, and this is close to guessing. And of course, the conclusion is that networks works better than human. And finally, one more slide. We tried to after this study, we developed a compact diagnosis system based on Raspberry Pi microcomputer, and you can see here approximately this small compact diagnosis system price 100 times smaller than this initial stationary basic diagnosis system, and we suppose that their abilities, they can work with the same accuracy, I suppose. So I think that will be all. Thank you for your attention. I would like to answer.